Let us continue p block elements, in which we will take boron family. We will take first. We will see what are the elements present in the boron family. Boron family contains boron, aluminum, gallium, indium, thallium. Electronic configuration of these elements we will see. Boron electronic configuration is helium 2s2 2p1, 2s2 2p1. Next, aluminum. Aluminum electronic configuration neon 3s2 3p1. Next, gallium. Gallium electronic configuration argon 4s2 4p1. Let us see whether gallium electronic configuration is correct or wrong. Now we will see the atomic numbers of these elements. Boron atomic number 5. Add 8, you will get aluminum 13. Now you have to add 18. Why? Because before gallium, transition elements present in that 3D series, 10 elements present, scandium to zinc. Therefore, we have to add 18 into this, then we will get atomic number of gallium is 31. So, before gallium, what is there means transition series 3D series elements are present. 3D series contains 10 elements from scandium to zinc. Therefore, we are adding 18. Otherwise, 8 we would have added. Because of transition elements, we are adding 18. So 31 is the atomic number. Argon atomic number 18. It is 2, it is 1. Therefore, totally 21. So 21 goes away in the sense remaining how much? 10. That 10 is for 3D series, 3D 10. So we have to write 3D 10, we have to write. So remember that gallium electronic configuration is argon 3D10 4s2 4p1. Next we will go for indium. Indium is a krypton 4D10 5s2 5p1. So before indium, transition elements 4D series present. 4D series elements present. Yttrium to cadmium. Yttrium to cadmium 4D series 10 elements present before indium. So that configuration is like this. Next we will go for thallium. Thallium electronic configuration xenon 5D10 6s2 6p1. This electronic configuration we have to check. We have to see the atomic numbers. We will see for these elements. Here 31 we said. To this we are adding 18. We are getting indium atomic number. To the indium we have to add 32. We have to add, then only we will get thallium. We will get. Why we should add 32? Because before thallium, what is there means transition elements are there. 5D series transition elements are there. 5D series contains what means lanthanum to mercury. Lanthanum atomic number how much means 57. Mercury atomic number how much means 80. 57 to 80. Is it 10? No. Now, hafnium we will take, it is 72. So, now in the 5D series, lanthanum is one element, then hafnium to mercury 10 elements. 57 to 72. What is the difference? 58 to 71. This is what means lanthanides, 4F series elements. This is 14 elements present here. Therefore, we are adding 32 to this in order to get a atomic number of thallium. So thallium atomic number this much. We have added how much? 32 we added. So This 4f series, that is 4f14, we have to write here 4f14. So thallium, in the sense, in this before this thallium, what is there means 5d series elements are there, that is 10. In that 5d, between lanthanum and hafnium, that is cerium to lutetium, 14 lanthanides present, 4f series elements present, 14 lanthanides present. Therefore we are writing 4f14, we are writing. So thallium electronic configuration xenon 4f14, 5d10, 6s2, 6p1, like this we can write. So we have written electronic configuration for boron family elements, we have written. Next we will see atomic radius. Atomic radius of these elements, that we will see. Now we will go for atomic radius of these elements. Down the group, what happens to the atomic radius? Increases. Okay. Now boron atomic radius is 85 picometer. Aluminium atomic radius is 143 picometer. So from boron to aluminium, atomic radius increases. Then gallium atomic radius, we will see. Gallium atomic radius is 135 picometer. Next, indium atomic radius is 167 picometer. From gallium to indium, atomic radius increases. So down the group, atomic radius increases. Then thallium atomic radius 170 picometer. So indium to thallium also atomic radius increasing. So is there any exception? Is there any exception here? That is aluminium to gallium exception. Generally, down the group, atomic radius increases. But aluminium to gallium, atomic radius is showing exceptional behavior. What happens here in the sense? It is decreasing. Why it decreases? Is there any factor? Now, atomic radius is determined by which one? Atom possesses particular radius. That radius is determined by which one? One is electronic configuration, another one is nuclear charge. What are the factors playing a role to determine atomic radius? One is nuclear charge. Nuclear charge means charge of nucleus. That means protons. Next one is screening constant. That means screening effect. Screening effect means electrons, electronic configuration. So screening constant. Cumulative effect is effective nuclear charge. Effective nuclear charge is equal to nuclear charge minus screening constant. Cumulative effect. Cumulative effect, what means? Effective nuclear charge. Effective nuclear charge is equal to nuclear charge minus screening constant. Next, number of shells. Number of shells filled with electrons. Okay. So now we will see nuclear charge. Nuclear charge increases means atomic radius decreases. Screening constant increases means atomic radius increases. Effective nuclear charge increases means atomic radius decreases. Number of shells increases means atomic radius increases. Isn't it? Now, down the group, what happens to the number of shells? See, increases, therefore radius increases. That's what we have seen here. But aluminum to gallium, we cannot consider this number of shells. Number of shells is not the dominant factor. Aluminum to gallium, number of shells increases, but that is not the dominant factor to say radius. So number of shells we will leave it. So effective nuclear charge you will see. Nuclear charge, what happens? Aluminum to gallium, no doubt increases. Atomic number increasing, therefore number of protons increasing. So nuclear charge increases. Sorry, nuclear charge. Screening constant. Screening constant depends on number of electrons. Now see number of electrons 13, here 31, therefore screening constant also increases. Say, effective nuclear charge. Effective nuclear charge must increase, then only radius will decrease. So what is the dominant factor in the sense effective nuclear charge here? Effective nuclear charge increases, therefore radius decreases. Sorry. Effective nuclear charge increasing. That means aluminum to gallium, nuclear charge increases. Screening constant also increases. Screening constant increases, but increase in screening constant is not much as like increasing nuclear charge. Then only effective nuclear charge will rise. Why increase in screening constant is not much like a increase in nuclear charge? Because here 3D is there. What is the order of screening effect? Screening effect order is S is greater than P, P is greater than D, D is greater than F. So D is showing poor screening effect. Therefore, increase in screening constant is much less when compared to increase in nuclear charge. Because of 3D10 shows poor screening effect. Due to poor screening effect, what happens means increase in screening constant is not much as like increase in nuclear charge. Therefore, radius decreases. So that in gallium, aluminum to gallium, why atomic radius decreases? Because 3D10 shows very poor screening effect. 3D10 shows poor screening effect. So this exceptional case, remember that aluminum to gallium, atomic radius decreases. It is exceptional case, exceptional behavior. Why atomic radius decreases? Because 3D10 shows very poor screening effect. 3D10 shows poor screening effect. Okay, so conclusion is what? Aluminum to gallium, atomic radius decreases. Reason is D10, 3D10 shows poor screening effect. Okay, next. Is there any other exceptional cases in this family? Is there any other exceptional cases? That we will see. Now, we will see from indium to thallium. What happens to the atomic radius? You see, indium to thallium. Indium to thallium decreases, that is increases how much means just 3. How much atomic radius increases from indium to thallium? Just 3. Why? Because 4f14 shows very poor screening effect. 4f14 shows very poor screening effect. Therefore, atomic radius increases very slightly. So, in the boron family, in the atomic radius, what we have to remember? What exceptional case we have to remember? One is aluminum to gallium, atomic radius decreases because 3D10 shows poor screening effect. Another exceptional case is indium to thallium, increase is very much low, that is 3, because 4f14 shows very poor screening effect. These two we have to remember. Okay, it is about atomic radius. Next we have to go for ionic radius. For going for ionic radius, what we have to see? First one, in the sense, first we have to see oxidation states. First we have to see oxidation states of boron family elements. What are the common oxidation states? That we have to see. Sir. Now, boron compounds we will see. Boron compounds is, one example is B2O3. One example for boron compound is B2O3, boron trioxide. Next example is metaborate. Now boron compound is B2O3. In B2O3, what is the oxidation number of boron? Cross multiply. You cross multiply, you will get oxidation number of boron, that is B3 plus. Then BO2 minus, metaborate. In metaborate, this boron is coming under how much means plus 3, metaborate. Then you see boron trifluoride. In boron trifluoride, this boron is plus 3. Then we will see magnesium boride. Magnesium boride. Magnesium boride in which boron is minus 3, that is Mg3B2. Magnesium boride, boron is minus 3. So boron shows what oxidation number means minus 3, otherwise plus 3. So positive oxidation state means plus 3, negative oxidation state means minus 3. Then orthoboric acid, H3BO3, orthoboric acid. Here boron oxidation number is plus 3. Borox, Na2B4O7.10H2O, borox. Here boron oxidation number is plus 3. Like this, in the boron compounds, boron shows plus 3 oxidation number. In the borides, boron shows minus 3 oxidation number. Then aluminum compounds, aluminum sulfate, aluminum chloride, aluminum nitrate. In this aluminum oxide, in this aluminum shows plus 3 oxidation number. Aluminum shows plus 3. Sorry. So oxidation numbers of aluminum we have seen. Then we will see thallium. Thallus chloride. This name is what means thallus chloride. Thallus chloride. Now TlCl3. Thallic chloride. Thallic chloride. Now thallus chloride and thallic chloride we have seen. Here thallus chloride, thallium plus 1. Thallic chloride, thallium plus 3. Thallus oxide, thallus oxide, thallic oxide. Thallus oxide, thallium is plus 1. Thallic oxide, thallium is plus 3. So we have seen regarding thallium, thallus and thallic. So thallium case plus 1 plus 3 possible. So in the plus 1 and plus 3, what about stability? How the stability is there? Stability is plus 1 has higher stability when compared to plus 3. For which case means for thallium. Thallium shows plus 3 compounds and also plus 1 compounds. Which is having higher stability means plus 1 stability is more when compared to plus 3. So, what about boron? Is it showing plus 1 or not? No. Boron shows only plus 3. In the borides, minus 3. Aluminum shows only plus 3. Gallium shows plus 1 and plus 3. Indium shows plus 1 and plus 3. Thallium shows plus 1 and plus 3. Okay. That means why boron is not showing plus 1? Why aluminum is not showing plus 1, but the rest are showing plus 1? What is the reason? Then in thallus chloride, in thallium, plus 1 stability is more when compared to plus 3. What is the reason? In thallium, +1 stability is more when compared to +3 stability. Why is it so? That we will see. Then boron shows -3. What is the reason? Boron is a metalloid, so non-metallic character is there. Therefore, it is gaining 3 electrons. So it shows -3 oxidation state. Sorry. Rest of the elements are metals. Therefore, they are not showing negative oxidation state. Even this metals also shows negative oxidation state in some cases, but that is rare. That is rare cases. Sorry. Now we will see this is general oxidation states for boron family elements is +3 and +1. Why thallium shows +1? That we'll see. In the thallium, this 6p this valence shell configuration is 6s to 6p1. 6s to 6p1. It is a ground state configuration. In the ground state configuration, 6p contains 1 electron, 1 unpaired electron. This unpaired electron involves in chemical reaction. Therefore, thallium shows +1. In the same way, indium, then gallium. Now we will go for excited state. Excited state means 6s electron goes to 6p. 6s electron goes to 6p. Now unpaired electrons 3. 3 unpaired electrons involved in chemical reaction. Therefore, thallium shows +3 oxidation state. Sorry. Regarding thallium converting into +1 because 6p electron. For that, we will see the potential. Potential is how much for a converting into +1? That is 0.34 volt. Converting into +3, that potential we'll see. Converting into +3, that potential we'll see. Converting into +3, that potential is this much. Now see, converting into +1, that potential is positive. Converting into +3, that potential is negative. This potential is experimental value. Experimentally obtained this one. This indicates that +1 stability is more, +3 stability is less. Okay. So +1 stability is more, +3 stability is less for which one in the sense? For thallium case. Why +3 stability is less? That means getting like this excited state is difficult from this ground state. That's why. Why getting excited state is difficult? That means unpairing 6s electron is difficult. Unpairing 6s electron is difficult because of 4f14 very poor screening effect. So 4f14 shows very poor screening effect. Therefore, between thallium nucleus and 6s electrons, strong attraction is possible. So 6s electrons are strongly bounded. Therefore, 6s electron is difficult to go for unpairing. Therefore, getting excited state is difficult, so that thallium +3 stability is low when compared to thallium +1. That means 6s electrons is almost unable to go for unpairing. It is going, but difficulty is more. Unable to go for unpairing. Therefore, it is 6s electrons is not interested to go for unpairing. 6s electrons is not interested to go for chemical reaction. So 6s electrons likes to be as inert, and it is a pair of electrons, therefore pair effect, inert pair effect. So due to inert pair effect, thallium has higher +1 stability when compared to +3. So why thallium +1 stability is more than +3? Because of inert pair effect. Why thallus is more stable than thallic? Because of inert pair effect. Inert pair effect is due to what? 4f14, very poor screening effect. Okay. So regarding thallium, we got an idea. What about in the case of indium? Indium shows which oxidation number? +1 and +3. Sorry. What about their stability? That we'll see. In the indium case, indium into indium +1. For that, E naught value is plus 0.18 volt. Plus 0.18 volt. Indium to indium +3. For that, E naught value is plus 0.34 volt. Plus 0.34 volt. So E naught for +3 is more when compared to E naught for +1. Therefore, +3 stability is more when compared to +1 stability. Therefore, for this +3 stability is more when compared to +1. In the same way, gallium +3 stability is more, +1 stability is less. Aluminium, boron only +3, no +1. Therefore, in these cases, +1 stability is more for which one? Means thallium. Indium and gallium +3 stability is more. Sir, why indium shows